Really excited to be here. Also for the hike. And today I'm going to tell you a little bit about this line of work that I've been very interested in for the past 3 to 4 years. And over time, this has become a collaboration with a number of amazing people. Let me tell you a little bit about them. So Umar is a PhD student at Berkeley. Venkat, my colleague. Tim and Peter, my amazing students at CMU. Siddhant was a student at Berkeley and now postdoc at MIT. And David and Benny are at ETH Zurich. Okay. Right. So, the title of this talk has the word method in it. So I should explain to you what is this method for. So at a at a very high level, this is a method to solve certain problems in extremal combinatorics. Okay. So of course that's super general, and in particular the connection to this workshop is very unclear. So let me explain to you the connection, and I'll do this by doing a bit that I've gotten used to when I give this talk. So many of us have lectured in a course called Theory of Computation or equivalent, and there is a very nice class in this course when we introduce our students to the KSAT problem. We tell them that KSAT is really an important problem. You can reduce every problem in NP to KSAT, and if you are imaginative or somewhat careless, you might also mention that in principle, you can take any mathematical conjecture and then easily construct a KSAT formula such that you can decide the truth of the mathematical conjecture by simply verifying whether the formula is satisfied. And therefore, KSAT can be used to do everything in math. In particular, KSAT is the only problem to study. Of course, this is rather glib, and we might even leave the class and laugh a little bit. But the punchline of today's talk is that for certain class of problems, this is exactly what I'm going to do. Okay? So the idea of today's talk is to solve problems in extremal combinatorics by somehow reducing them to verifying the unsatisfiability of certain XOR formulas. These XOR formulas will be randomish. And I'll explain what this means, as the talk goes on. But, let me give a more than one-line description of what, this little, sequence of works has become about. So, we're going to be interested in problems which ask for verifying whether a certain combinatorial object satisfies some additional nice combinatorial property, right? This talk is going to be about a very concrete example about certain problems in coding theory. We'll be interested in whether codes have some extra property called local decodability or local correctability, right? So that's you might imagine, but right now let's stick to the abstraction. What we will do is associate to this combinatorial object a family, not one, a family of KSAT formulas with a property that if this combinatorial object does satisfy this nice property you're looking at, then every member of this family of KSAT formulas is satisfiable. Okay? So if I now want to prove that this object does not exist, there is a rather simple plan. I simply need to show that there is at least one member in this family which is unsatisfiable. Right? So far, it's wacko, but perhaps legit. Right? Now, the question is which member of the family should I work with? Well, the idea is very simple. I'm actually going to work and try to show that a random member of this family is unsatisfied. Okay? What's the idea? Well, we've studied random KSAT formulas for a while. We know lots of tools for them, not just for proving lower bound, but also for proving non-trivial upper bounds on certificates for random KSAT formulas. So one might expect that maybe we can draw on our understanding of random KSAT and when certificates exist and so on and so forth, to somehow prove that this random member of this particular family is unsatisfiable. There's of course a gap here because this is a random member from some wacko family I constructed. It's not going to be random KSAT, but nevertheless, that's the idea, right? Well, there is a issue with this plan right off, which is that in all the applications I'm going to tell you about, the number of random bits that are required to sample a member of this family will be way fewer than the number of variables that this formula will be on. Why does that hurt you? Well, if I give you a random formula, one way to prove it's unsatisfiable with high probability at least, is to simply do a naive probabilistic analysis, do Chernoff plus union bound, whatever, right? If you wanted to do this, you might have to do a union bound on 2 to the n possible assignments because n is the number of variables. And for this to work out, you will need a tail bound, which looks like 2 to the minus n. But if the number of random bits is like k, which is much less than n, this tail bound will never be true. So, this is like, at least a very intuitive high-level objection to why you cannot hope to do naive probabilistic analysis, okay? So then what? So the punchline is that even though this naive probabilistic analysis will, in general, fail, we will be able to take the certificates that we have analyzed for random K-SAT formulas and some generalizations of them that I call semi-random K-SAT formulas and show that these certificates are actually powerful enough that we can argue their existence even for these randomness starved formulas. So even though, I cannot do naive probabilistic analysis and verify unsatisfiability, I'll actually prove unsatisfiability by showing that some certificates of unsatisfiability exist. And these somehow, I can argue with very little randomness. So this is the overall plan. I don't expect you to understand, how this plan is going to work. It can look very wacko. I hope it looks wacko. But, I'm going to explain by means of an example how this is all going to work out. Yes?
XOR formulas are just systems of linear equations.
Linear equations. In fact, I'm going to look at sparse linear equations. Like,
so why do we talk about SAT at all? I mean, the satisfiability problem.
So by SAT, I just mean satisfiable.
Yeah. Okay. So
sorry.
Okay. It's you just.
Sorry. My abbreviation is throwing you off. I just mean a family of XOR formulas is satisfiable.
Okay.
That's all. Good. Yes. Feel free to stop me with questions anytime. Okay. Good. All right. So I like this because I think it's a rather surprising, at least to me, application of ideas in proof complexity to making progress on problems in combinatorics and coding theory. Okay. Good. So let me tell you a little bit of a story of how this whole line of work arose, and then I'll get back to some more concrete math. So in some sense, we were looking at a question which was really asked by Hsieh, and Hsieh was motivated by the questions of whether the kind of certificates we have shown exist for random K-SAT formulas. He was like worried that these are like overly tied down to the specific random model we are looking at. So he was asking the question of, well, do they work if I relax the random model a little bit? Do they work if I have lesser randomness? Do they work if I have a more general model of randomness? And in order to pose this question, he asked this, concrete problem of like refuting smoothed K-SAT formula, which I will not define for you right now. Okay, and for a while, I guess nothing much was known about this problem until we were doing some application of proof complexity to attacking certain assumptions that arose in the context of cryptography. And for this, we needed to upgrade the guarantees of some of these random K-SAT algorithms to slightly more general versions. And that's the time, I got interested in this problem. I did not know like how to attack the most general question of Hsieh at the time. But basically, over time, with a bunch of other co-authors, that's exactly what we figured out. So it began with, this work with Venkat and our student at the time, Jackson Abascal. And then this was really, in some sense, completed in this work with Venkat and Peter Manohar, who is, my graduating PhD student. He's amazing. And then we found a slightly simpler proof of the same result with my other student, Tim, and Siddhant Mohanty. So, basically this result shows, which I'm not going to tell you much about today. It shows, why the smooth formulas that Hsieh considered as like a significantly general version of random K-SAT formulas are in fact no harder than random in the sense that you can build different certificates that achieve the same guarantees that we know for random. So that was like, basically the proof complexity work, so to speak. And, over time, I should tell you, these certificates are based on, certain spectral methods. And, these spectral methods are what I'm going to explain to you in this talk. They're based on like certain matrices or Kikuchi matrices. Kikuchi word is, something I can only tell you 2 lines about. It's actually named after a physicist, Ryoichi Kikuchi. Somehow Vine, Alaoui, and Moore were interested in a problem in statistical inference called Gaussian tensor PCA. And they made this connection that somehow, there is this quantity that Kikuchi, the physicist, was studying. And if you look at the Hsieh of this quantity, there is some class of matrices that fall out. These matrices are actually, in retrospect, rather simple, and I'm going to define them for you very soon. But that is how, in some sense, we came up with it, or at least they came up with it in the first place. And so we are sticking to their terminology here. Okay. So really, like in some sense, now we use the term loosely because there are various versions of these matrices, all have like some underlying theme. And I'm going to explain that to you later on. But this is just some loosely defined term now. It's not like a very specific term for a specific matrix. Anyway, all right. So what has happened since then, is we've used these certificates that we now know exist for smoothed k-SAT formulas for applications in combinatorics and coding theory, which is what this talk is about. Okay, so I'm going to tell you like a little bit about what applications we know so far. So the first application we did was confirming a certain conjecture of Hsieh from 2008 on a certain Moore bound. So these are like questions about what is the length of the smallest cycle in a graph or a hypergraph when it has a given number of edges or hyperedges. And so for graphs, this question was settled, but for hypergraphs, it was a conjecture due to Hsieh, and we were able to confirm this conjecture. And later on, we found a simpler proof in this work with Tim, Siddhant, David, and Benny Sudakov. And then, today's talk is about these two applications to lower bounds, for certain special class of codes that arise in coding theory. So these are like locally decodable codes for which we proved a lower bound last year with Omar and Venkat and Peter. And then, very recently, about 3 months ago, with Peter, we proved this exponential lower bound on locally correctable codes. I'll tell you a little bit about this result also today. There's also an application to, strong forms of Semiradis problem, which, ask for like showing that there is an arithmetic progression in any dense subset of integers. Some of you may have seen this. It's like a interesting, important question in math. And it turns out that there is some extension or strengthenings of it, that people have studied, and you can actually improve the bounds in the strengthenings by using the same kind of ideas. This I will tell you nothing about today, but of course, feel free to ask me offline. So, like I said, and there are some other applications very recent to, solving some planted CSPs, which also I will not tell you about. Today, I'll tell you about these applications to, coding theory. In fact, my plan is to tell you essentially a complete proof of a special case, for 4-query locally decodable codes. Hopefully, I can actually get to the end for this. It's rather simple, but I think I can hopefully also convey the whole idea to you. Good. All right. So any questions before I dive into the specifics? Good. Excellent. So, let me, tell you some basic coding theory, mostly like a recall, hopefully not too boring. And, then I'll come back to, what local codes are and all. Okay. So, coding theory 101, maybe the first class, right? So what's the idea? Well, we want to take a k-bit message. My bits will always be plus or minus 1 in this talk, right? I want to stretch them to a longer string of n bits. Okay, so k will always be my message length, n will always be my code word length. And the map that sends b into this code word, I'm going to call e for encoding. Okay, so a code is simply like an encoding map like this that sends every k-bit message into an n-bit code word, right? What's the idea? Why are we doing this? Well, because we imagine that we are going to somehow transmit this code word, which will suffer corruptions along the way. So really in some sense, this person that we're transmitting some message to will receive a corrupted version of this code word, which I'm going to call y. And I'm going to call the process delta corruption, which simply means that delta fraction of the coordinates are flipped. Okay, think of delta as a tiny constant throughout this talk.
Exactly delta for less or equal
to delta. Yes. So at most delta fraction corruptions, that's the model. It's worst case corruption model. So any delta fraction of the bits can be corrupted. There is no distribution or whatever on this. Okay, good. So now what's our goal? Our goal is basically to decode. Our goal is to give. So encoding map is not enough. Our goal is to provide a companion decoding map that takes this corrupted code word and still reliably gets back the intended message I needed to send without any errors. Right? This is the basic problem in coding theory. So what does the decoder really do? Well, a standard decoder takes input such a delta corrupted version of a true code word, and it's supposed to somehow extract for me the B that I intended to send. Today, I'm going to be interested in a very, very simple kind of decoding algorithm. And the question we are interested in is, are there codes that admit such ultra simple decoding algorithms? Okay, so let me explain what these super simple decoding algorithms are. I'm going to call them local decoding algorithms. Okay, so this simple kind of a decoder not only takes the corrupted version of a code word, it also takes as an additional input one of the bits of the message. And you should think of the goal of the decoder as taking input y and this bit I and telling me what is the ith bit of the message. So the decoder is like, trying to decode one bit of the message at a time. Okay. So far, there is nothing new. Any decoder can be thought of this way, but there's more coming. Now, what is the simplicity aspect of the decoder? Well, the decoder is actually allowed a very simple restricted access to the corrupted code word. The decoder can only make so-called Q queries to the corrupted code word. And think of Q as very, very small. In fact, this whole talk is about Q equals 3. So the decoder's job is to read 2 or 3 bits of the corrupted code word and get back to me reliably the ith bit of the message that I intended to send. Yes? Great. Now, as you think about it, there is a big problem. I have delta fraction corruption. So like 1 in 100, let's say, bits are corrupted, but I'm only allowed to read 3 bits. Well, if there are some fixed 3 bits, the adversary has plenty of budget to corrupt, those 3 bits permanently, and then I will never be able to do this. What this proves is that there cannot be any deterministic local decoding algorithm. You obviously need randomness, right, in order to somehow, thwart this basic adversarial strategy. So my decoders will always be randomized algorithms, and all the probabilities will be over the randomness of the decoder's coins. There is nothing else that is random in this whole process. And our goal, now, there's going to be probability of error because there is randomness. Our goal is to extract the bit b sub I with tiny but fixed constant advantage over random guessing. Okay, so I want to get b sub I back correctly with probability half plus epsilon for some fixed constant epsilon.
So is this a non-adaptive query or adaptive?
Excellent question. It won't matter is the answer. Like, in this world, because the number of queries is a constant, by using something on epsilon, like going from epsilon to epsilon over 8, you can always assume that the decoder is non-adaptive.
For the probability, the worst case probability of all i's would be at least, right?
Yeah, so let's understand this carefully. Yes, Antonina's question is very important. The inputs to the decoder are worst case. I is worst case, Y is worst case, only subject to the constraint that it is a delta corruption of some code. The only probabilities are over the random coin tosses of the algorithm. Any other questions? Yes.
Yeah, just to follow up. I mean, for a specific queue, like 3 or 4, it matters, right? Whether it's enough.
No. So I don't increase the number of queries in this world. I only drop the correctness probability. So I can change epsilon to epsilon over 8. No change in queries. Good. Any other questions about the definition? Yes.
You said you're interested in small values of Q.
Yes.
But still, if Q grows, we can expect the error probability to fall to 0 or what?
Right. Excellent. So let's also talk about this. One way to somehow make the error probabilities arbitrarily tiny is to amplify, like we are used to. So if I give you a 3-query algorithm, you can just run it a few times, increase the number of queries, and make the fidelity as high as possible. There is also more direct methods to achieve this, but I will not focus on that. This talk is only about getting a constant advantage, right? So we'll not worry about too much about this amplification, etc. Good, excellent. All right, so I'm going to call this a Q delta epsilon local decoding algorithm. Q for number of queries, delta for the fraction of corruptions it tolerates, epsilon for the advantage it gives on random guessing. Good. All right. So now what I'm going to do is, tell you about a random factoid from coding theory, because I want to talk about a slight generalization of local decoding. Okay. So, also, this talk, delta and epsilon are small fixed constants. We will never worry about them. This is the most interesting and well-studied setting. That's the only thing we are going to focus on. So from now on, you can just assume that delta and epsilon are 1 in 100. Okay. Good. So this random factoid is the following, that if the encoding map E is linear, so when you view the messages and the code words as F2 to the K and F2 to the N, in this world, if the map E happens to be a linear map, so F2 linear map specifically speaking, then you can assume without the loss of generality that the code is so-called systematic. What that means is that the first K out of the N bits of the code word simply copy the message. Okay. In fact, a version of this fact is true even for nonlinear codes, but I will not tell you about that today. Okay, because this talk is almost entirely about linear codes, even though the results I'm going to talk about extend to nonlinear. Good. So equivalently, you can think of a local decoding algorithm as being able to correct any of the first k bits of the code word. Yes. Once I pose this, you can ask, are there algorithms that can correct any bit of the code word instead of just the first k? That leads us to the definition of a local correction algorithm, where the only difference is that the input to the decoder or corrector, so to speak, is not an arbitrary bit in 1 through k. In fact, it's an arbitrary index in 1 through n. I'm interested in correcting any of, one out of the n possible bits of the code word. Many of them are corrupted, remember? But I want an algorithm that can somehow, query some 3 other bits of the code word and reliably, tell me what that bit should have been. Any questions about this?
So now you're convinced us that locally correctable is therefore clearly at least as hard as.
Yes. The logic of telling you the random factoid was that local correction is a strict generalization of local decoding, or at least formal generalization. This whole talk is about how different are they, but we'll get to that.
But aren't you losing the whole point of coding theory? I mean, now you have no advantage of strengthening, of lengthening the word, because now you want to correct. Now, what is the information that now you just have n bits that you got sent?
No. So let me say a different thing. If you don't ask for local decoding, then correction and decoding are equivalent. Any method that can recover the message reliably also recovers the code word correctly, because I can just compute the encoding map myself. The whole difference, if at all there's a difference between them, it has to be because of localness. Otherwise, decoding and correction are equivalent. Without the locality property, they are equivalent.
Yeah, but now you want to correct any of the n bits,
Yeah.
right? So that means, I mean, what is the advantage of knowing that this was a map from like?
It's a restricted map, right? Not all possible n bits are possible. There are relationships between them. So the point is that even if I correct delta fraction, I can recover information about what they should have been by looking at the other bits, because it's a highly constrained map.
Okay.
I have a similar question to Greg's. So now actually the mapping E is no longer important. You are just interested in the set of possible code words, right?
Yes, that's a different way to say the correct thing. But the set of code words is a highly restricted set. It's a very small subset. It's only 2 to the k code words.
Small, yeah, but
Yes.
But still, E is not important any longer.
E is not important. Yes. Any other questions? Good. Excellent. So yeah, I guess this is the point I already made. And I want to tell you much about applications. I'm going to spend 30 seconds telling you what the applications are. So these are whatever, fundamental objects. They have a long history. They first arose in the context of constructing probabilistically checkable proofs. In fact, the codes I'm going to talk about were the ones responsible for the earliest PCPs. Since then they've found lots of applications in private information retrieval, reducing worst case problems to average case ones, distributed computation, etc., etc. I won't tell you anything about that. Hopefully you like coding theory enough and local decoding and local collection enough to enjoy this talk for what it's about. Yes.
Can you say 2 sentences? Is this close to list decoding?
No.
Okay.
Good question, but no. So list decoding is about relaxing the notion of unique decoding. So unique decoding means that I just want to recover the message uniquely. We are often in a setting where the number of corruptions is large enough that this is not possible. But it turns out there's a non-trivial regime where we can construct a small list, even though we cannot uniquely determine what the message was. This is unrelated to what we want to do today, because we are interested in unique decoding, but local decoding. Excellent. Good. All right. So I told you all these fancy definitions, but the main question we are interested in today is, are there these objects, right? And I want to tell you that this is a purely combinatorial question. It's not a question of explicit constructions. It's not a question of efficient algorithms. I'm simply asking, is there any map in the world E that admits a really, really simple local decoding algorithm, right? It's a combinatorial question, nothing algorithmic here, right? And the reason this is interesting is because the standard way to prove existence results in coding theory is out of the window for us. Shannon in 1947 showed that there are good codes. You can stretch a message by only constant factor and decode constant fraction of errors. And he could establish this by simply arguing that a random code is good. There is no natural random, there's just no random model known for local decoding or local correction. So even to show that these objects exist, we've got to do some magic algebra or number theory, okay? So let me tell you what we know about these objects, whether they exist or not, okay? So I'm going to tell you the story until 2023, and then I'll tell you the update that we have. So q equals 1, as you can all imagine, intuitively at least, there is nothing possible. So q equals 2 is the first interesting regime. And here we actually have a simple code. One of the first codes you study in a coding theory class, perhaps class 2, called the Hadamard code, that stretches k bits to 2 to the k bits, exponentially so, and actually is 2-query locally decodable. In fact, not just locally decodable, it's also 2-query locally correctable. Okay, so it's a linear code, and I'll just say one line about it if you haven't seen this. This code views the message as a coefficient vector of a linear function, and then simply the code itself evaluates the linear function on all possible points in f2 to the k. That's what the code is. Okay, and then by basically viewing this object as like evaluations of linear functions, there's a very simple algorithm that can decode it. The idea is that 2 points uniquely determine a line. That's basically the idea for 2-query local decoding. In fact, it also works for local correction, and that's already a proof that there is a non-trivial locally decodable code with 2 queries. Right? Now, you might think that this is rather atrocious. I'm blowing up the message length by exponential amount, but it turns out that this is also the best we can do. We know lower bounds. So, this quest for proving lower bounds was begun in this very beautiful work of Katz and Trevisan about 24 years ago. And things that built on their work eventually basically established that nothing better is possible. Actually, nothing better is possible even if you drop linearity. Even nonlinear code, even amongst nonlinear codes, this is the best, but linear codes are enough for us. So the story for q equals 2 is basically complete. So what should we do? We should talk about q equals 3. That's what we'll do. There's a very natural upgrade on Hadamard codes, which actually gives a non-trivial improvement on Hadamard. So we viewed the message as coefficients of a linear function. If you view them as coefficients of a quadratic function, you get, and then just like report the evaluations, you get the generalization called Reed-Muller code, just the evaluations of low degree polynomials, degree 2 polynomials, so to speak here, that, by the same kind of interpolation idea is 3-query locally decodable and locally correctable. Again, it gives both local decodability and local correctability with basically the same idea. And it gives an improvement over Hadamard because the stretch is now 2 to the square root of k instead of 2 to the k. So it's like slightly better than 2 to the k.
Excuse me. This doesn't mean that you does this mean that you correct with 100% probability, or
the correction algorithm is always randomized. So delta and epsilon, in this talk are always some constants. So think of this algorithm as giving some.
you are saying that there are positive constants.
There are positive constants for which, 1 in 100 is like enough for us.
Does it scale if I increase q and take it now?
Yes.
It will scale, yeah.
Yes. So Sasha is like observing that one natural question to ask, and the answer is yes. You can increase q and change n to 2 to the k to the 1 over q minus 1, which is fits with the 2 data points you have over here. Right? So Reed-Muller in fact has generalizations, and it does give the trade-off exactly as Sasha predicts. Any other question? Good, very good. So now you can ask. Oh, sorry, I should not reveal the punchline too much. You can ask, are there better codes, right? We generalized Hadamard. Hadamard had no better analog, but what about the 3-query? And till about 2008, this question was like controversial. I tried to check my history with my colleague Zeb Dwin, who is an expert in this matters, and I asked him, what did people think? I said, okay, it was divided. Some people thought there is a construction, some people thought, Reed-Muller is the best, I don't know what to do. In fact, something magical happened in 2008. People proved that there is in fact a 3-query locally decodable code of sub-exponential length. So it's like this, fantastic paper of Sergei Yakhanin, which was improved on, by Efremenko. So Yakhanin's construction was like modulo the Mersenne prime conjecture, if you know what that is. There are infinitely many Mersenne primes. And then Efremenko came with like a sweepingly cool idea that removed all this Mersenne prime business and gave like an honest to goodness construction. This is a really beautiful piece of work. In one shot, it gets you a stretch of 2 to the 2 to the square root log k. Notice that it is tinier than 2 to the 2 to the constant times log k for any constant. So it is sub-exponential in the sense that it's tinier than 2 to the k to the any constant. Okay, it's in that sense, it's a sub-exponential stretch code. Okay, but they only argued a local decoding algorithm for this code. In fact, they did not know if this code itself is locally correctable. And this was posed as the open question, by Yakhanen in 2011 to just determine if this code is locally correctable, right? How do you answer this question? Well, you try to, prove lower bounds in general, like question of, whether there are better codes, etc., etc. But our best lower bounds in Q equals 3 are terrible. We had like a tight lower bound for Q equals 2, but once we got to Q equals 3, the same set of works are essentially the best known. Some logarithmic factors are improved later on, but the same set of works are best known results so far in at least 2023. And we know that n must stretch quadratically in K. Needs to be, it can't be linear, gotta be quadratic, and that's kind of the best we knew. It's a huge gap for both local decoding and local correctivity. Yes, Meera?
For local correction, do we know how many queries is enough for this code? 3 is not known, but.
Excellent question. No. Well, I'm going to answer this question in a roundabout way soon, but yes, no non-trivial result is known.
This assumption of linearity. So is it known that the best locally correctable or decoded codes have to be linear? Or
no, but in some sense, all our constructions are linear. There is literally no nonlinear code I know.
But the low bounds never use linearity. They just go.
Some did.
So yeah, the initial lower bounds were for linear. So like Katz-Trevisan and Goldreich, Karloff, Schulman, Trevisan were for linear codes, and then this work of Kanelidis and De Wolf made some connection to quantum and upgraded them to nonlinear. But in nonlinear is like a great sanity check, right? Like we don't want to leave a code hanging on the table, so to speak, right? Like even though we don't expect it to be, we want to be maybe certain. Good. So that's the status of the world. And now I can tell you what what upgrades we have. Oh, I should tell you one more thing. Complexity theory, as we all know, is a very introspective field. So when we fail to do things, we actually try to find out reasons for our failure, which is what also people did. So they tried to figure out what is it that is blocking us from proving better lower bounds, and they identified like a barrier. So like it's a very nice paper of Vir, Gopi, Gu, and Victorson, built on by Alrabiah and Guruswami. They basically showed that there is some structure called spanoid, which generalizes, LDCs and LCCs, and they proved that all these ideas for lower bounds apply more generally to this structure, for which the lower bounds are tight. So this was an explanation for why we are getting stuck on, finding a better lower bound. And then, this work of Barkol, Hsieh, and Weinreb made a connection to this, widely open conjecture from the 1970s in design theory. It's called the Hamada conjecture. It's about, whether optimal designs, what is the structure of optimal designs? I won't tell you much about it today. But they showed that if you settle the question of is there a better than read mother code for 3-query local correction, then you will make, you will basically settle a case of Hamada. And then, their argument was that maybe this is why it's very hard, because it's a conjecture from the 70s, it's kind of hard to break, right? Anyway, you could also think of it as an optimistic thing that if you do this, you also get something about Hamada, whatever. Excellent. So now, I can tell you what we did. So, we began this line of work, maybe a couple of years ago. And the first thing we did is we upgraded the quadratic lower bound for 3-query local decoding to cubic, right? Up to some polylog factors. So that was the result with Alrabiah and Weikert and Peter. And then very recently, we actually proved that for 3-query locally correctable codes, you can take this same quadratic lower bound. I should have said, by the way, the lower bounds before this work were all the same for local decoding or local correction. In fact, no separation was known between these two objects. And so this is the first separation between the result. And we in fact proved that for 3-query local correction, exponential block length is necessary. So, the exponential function is k to the 1/8, whatever in the exponent right now, but that's what we established. So just to make some, simple comments about this result, because there is an exponential length 3-query LDC, this establishes in particular that 3-query LDCs are strictly, weaker objects than 3-query LCCs. In particular, it resolves the open question of Yakhanen that their code is not locally correctable, at least with 3 queries. Yeah, that's that. And maybe it hints that it's not quite 2 to the k to the 1/2 yet. It's not matching read mother, but it's somehow saying that maybe you're kind of close. Okay, and my suspicion is that we'll be there in a few months. So I think we will know the right answer soon. Okay, so I'm talking about only f sub 2, but these results all extend to any small finite field. Right now, the techniques that we have a natural limit at 2 to the k to the 1/3. I feel like proving a better lower bound at 2 to the k to the 1/3 would likely require some non-trivial new idea that I don't have currently. But that at least is possible. And in fact, not only possible, it was achieved like a month ago or 3 weeks ago by Tal Yankovitz, who basically like figured out some optimizations and did it and was able to improve the 2 to the k to the 1/8 to 2 to the k to the 1/4. So like I said, wait a few months and maybe we'll know the right answer for 3 LCCs after all. Good. So any questions about this result? Excellent. Okay. So what I want to tell you now is how this result works. In fact, I won't tell you much about the 3-query local correction part. I'll explain how this correction to proof complexity arises, which is like my main intention for this workshop. So I'm focused on proving lower bounds for locally decodable codes. And instead of like this result on 3 queries, I'll actually prove to you the result for 4 queries. Okay. And the 4 is because it's the smallest even number bigger than 2. If you worked at all on problems like this, 2 is easy, odd numbers are hard. So I'm selecting the least even number bigger than 2. Okay. So I'm going to explain this whole idea with 4 LDCs, and I'm going to restrict to linear things, even though these ideas extend to non-linear things. And I'll tell you, how to somehow go from 4 LDCs, this combinatorial question, to a family of XOR formulas which are satisfiable, and then like refute them. Okay. Good. And then I'll tell you like some basic heuristic that underline this line of work, and tell you like why that suggests at least a nugget of an idea for this 3-query locally correctable code lower bound, but not really much in detail today. Good. All right. So let's go to this first milestone of trying to take a locally decodable code and make some satisfiable set of XOR formulas out of it. To do this, I'm actually going to give you some combinatorial characterization of a Q-query locally decodable code. Okay? These characterizations are actually obtained by very simple considerations, but I would be sketchy about them. Right? I would argue to you, but not really formally. Okay? So this is like trying to infer some combinatorial structure in what QLDCs must look like. All right, so let's think about what a code like this will do. Well, if I have to decode, let's say, bit number I, what will the decoder do? It has to query some set of qubits, perhaps chosen randomly, and then apply some function on these qubits. It's going to be a predicate, as in like it's a function that computes 0 or 1 or plus or minus 1 out, right? So first, I claim, without proof, that without loss of generality, the decoder can be taken to be non-adaptive. As in like, in principle, you could have like, queried these qubits in order, like take the first bit, look at the answer, decide the next bit, and so on. But it turns out, in this case, it is without loss of generality, and you can just like at one blush, give me all the qubits. Okay. So in this, because of this assumption, because of this basically without the loss of generality assumption, you can assume that the decoder for, let's say, ith bit is simply a collection of q tuples. Like I'm just saying, it's a uniform distribution on some set of allowed q tuples. That's my decoding set. Okay. So what I have over there, h1, h2, h sub k, are the decoding sets for each of the k message bits. Hi is just a collection of q tuples that correctly allow me to decode the first ith bit. Okay, good. Further, if the code is linear, the decoding algorithm, in fact, can be proven to be, without loss of generality, linear itself. What does that mean? The decoder does the following. If I'm decoding the first bit, I take a q tuple in the list, I just add the bits mod 2. That's it. That's my decoding algorithm. And this is all you can do. Moreover, and so this is like in notation, right? Like I'm working in the plus minus 1 basis. I'm working in the boards, where the bits are plus or minus 1. So adding mod 2 is like multiplying the bits out. So here is what the decoding does. If I want to decode the ith bit, I take a tuple C in h sub I, multiply the bits out of the code word, and I'm supposed to correctly get the message bit out. Now, this 3 is saying something more. It's saying that, if there is no error, if I like do this decoding on the true uncorrupted code word, then in fact, I succeed with probability 1. This is again without the loss of generality. Okay. Even though, my guarantee is for like, if I have delta fraction corruptions, I should recover with epsilon advantage. If there is no corruption without the loss of generality, I must correct with probability 1. Okay. All right. And, I in fact can argue the following. So, if I overly query one of the bits of the code word, you can imagine that I'm in trouble. Because, then the adversary has all the more motivation to corrupt this bit. Right? If I focus on one bit more than others, I'm in trouble. So you would imagine that, a decoding algorithm, if it has to succeed under constant fraction corruptions, must be smooth. It should not like overly query any single bit. You can in fact push this logic to the extreme and prove that again, without loss of generality, the q tuples I have are simply disjoint. So in any HI, any bit of the code word can be queried at most once. Okay, and notice that each of this, and that's basically what I call a hypergraph matching. It's a collection of disjoint set of q tuples. The number of q tuples must be large. In particular, if they're like tinier than like let's say delta n over 4, then I can corrupt all the bits queried for h sub I and I'm in trouble. So these must be large matchings, right? So anyway, so the combinatorial characterization we have arrived at so far is that without law of generality, I can assume that the decoder simply is an XOR function that is applied to one of the query sets that forms a almost perfect matching, like a omega n size matching. In fact, I'm gonna, for the purpose of the talk, simply make it a perfect matching from now on. Okay, this will change nothing in my proof.
I didn't get, why did you say that it's queried only, each position is queried once? You're not a bias, so maybe each position is queried twice.
Yes, exactly. But you can take any decoder that queries, let's say, all the bits equal number of times and extract from another decoder that does query exactly once, and the performance is not altered. Think of it like a distribution. Like I'm saying, I have a distribution that in the support, maybe I have like 2 points that query the same bit. But if I sample and I take like, maybe samples enough so that each bit is queried once, that's already enough for my guarantees. And if it's not clear, think of it like, an assumption. It's without law of generality here that we can assume that the decoding distribution is simply like a matching. You query, one of the q tuples, and those bits never occur again.
But you lose a few constant factors.
I lose a few constant factors. So in all these, adaptations, epsilon is changing from epsilon to epsilon over 100 over 3. Good. Any other questions so far? All right. So, now, you know what combinatorial description of local decoding looks like. While I have you, I can also tell you the combinatorial description of local correction. It's exactly the same, except I have this decoding sets not just for the first k bits, but for all the n bits. That's it. Nothing else changes. Any questions?
So is the distribution on members of this matching?
Yeah, so just uniform distribution. Any other questions so far? No. Okay, great. All right. So, next I want to take this combinatorial description and tell you what these XOR formulas are, right? We're going to somehow reduce it to refuting formulas. Actually, the formulas are going to be really, really simple. Okay. Given a collection of k matchings that purportedly describe a 4-query locally decodable code, I'm going to form a 4 XOR formula, okay, that simply encodes the following logical sentence. The formula encodes that for any fixed message, there is a code word. This is the assignment, so to speak, which passes all the local decoding checks. Okay. So in notation, for any message B, if I write down the following set of XOR constraints, so look at what these constraints are. I go over all possible k matchings. I go over all possible 4 tuples in each matching, and I add the constraint that the corresponding bits of X must XOR out or multiply out to the correct bit of the message, right? We know that if there is a code with this decoding structure, then for every message B, there is a code word, X, which will pass all these checks. In particular, that X is a satisfying assignment to the system of 4 XOR constraints, right? So you can see I've given you a family of 4 XOR formulas which are satisfiable whenever I start from a true code with the given matchings as decoding sets. In fact, my family has exactly 2 to the k different, 4 XOR formulas, and that's the size of the family. Any questions so far?
Where is the probability in this?
So far, there is no probability.
So at the moment, you've only said this works on uncorrupted things.
Yes.
You haven't said anything about what
Yeah.
what goes on for corrupted.
Yeah, so let me observe that if things work with probability 1 for corrupted, and I have matchings, then I claim that you actually get the corrupted version for free. Because what's the idea? If I query a random 4 tuple, because it's a matching, I will escape the delta fraction of the corrupted bits, with like, I don't know, some 1 minus 4 delta probability, right? And then, I have the guarantee. Okay, good.
I'm confused. So you are talking
Yes.
about 4 locally decodable.
Yes.
But on your picture, you have hypergraph.
Oh yeah, the picture is not to scale.
So they should be 4.
It should be 4. My bad. Yes. This talk is trying to do both 3 and 4 in the same thing, and I was lazy to make 2 diagrams. Sorry. Good. All right. So now you know what the XOR formulas are. And now you know, I'm going to call this formula just psi sub b, right? Like for every message b, I have a formula psi sub b. And you know, it's a system of constraints. We can even estimate how many there are. Each matching is n over 4 size. There are k matchings. So in total, there are nk over 4 XOR constraints on n variables. Yes? And you know, like we already observed, for any b, the system is satisfiable if I do start from a locally decodable code. Now, you know, I can tell you what the random formula is. Actually, you know, there's a very simple scheme for choosing a random formula. Choose a random message, take psi sub b corresponding to it, right? How many random bits do I have in this process? Well, k, right? But, you know, it's a code. K is obviously much tinier than n. Otherwise, we are doing something boring, which means that the number of random bits I have is always going to be much less than n. So this is like, you know, trying to justify the sentence I made at the beginning of the talk, that you're going to get a formula with way fewer bits of randomness than the number of variables. Okay? So how do I prove that such a code does not exist? Well, I have to take any set of k matchings. Then I take the system of 2 to the k, you know, XOR formulas, and I prove that no matter what the matchings, no matter what the perfect matchings, at least one of this family is unsatisfiable. That's enough clearly, right? That's proving that no matching would ever give you a 4 LDC, which means there is no 4 LDC. So you've seen like how I reduced the problem of proving that there is no 4 LDC with some value of k to simply verifying that, you know, one of these 2 to the k formulas is unsatisfiable. Make sense? Okay, good. All right. So, you know, I'll now tell you how to actually prove these formulas, this random formula unsatisfiable. Okay. Good. So, what we're going to do is, you know, for a like, you know, for every b, the formula is supposed to be satisfiable if there is a code. But for a random b, we will show that there is a certificate of unsatisfiability. Right? This is like, you know, eschewing this, you know, probabilistic analysis and trying to come up with like a certificate. And we'll show that, you know, in fact, this can be done with low amount of randomness. Okay, so, you know, towards this, let's build the following polynomial. What's this polynomial doing? Well, you know, I'm just taking all possible monomials corresponding to the decoding sets in H sub I and adding them up. So that's x sub c, the sum c in H sub I, multiplying them by b sub I, and then summing up over all the k bits of the message. What's going on? Well, you know, this polynomial, for any b, if I use the correct code word, it gives me a value of nk over 4. Because, you know, if x is the correct code word corresponding to b, for every c in H sub I, x sub c evaluates to b sub I, which means x sub c times b sub I is square of a plus minus 1 bit, so it's plus 1. So for every satisfied constraint, I'm getting plus 1, which means that this will be nk over 4, the maximum possible when this formula is satisfiable, right? Good. So, you know, what am I going to do? You know, I know that, you know, for every b, this formula has a large value, but I'll prove to you for random b, it actually has a small value. Okay. How am I going to do this? I'm actually going to write this polynomial psi sub b of x as a quadratic form of some matrix. Okay. This is the idea behind spectral refutation. So far, I've told you nothing new. We are still in 2002. But, you know, the idea is to somehow, you know, look at this degree 4 polynomial I have, interpret it as a quadratic form of some matrix, and then use some spectral upper bound on the quadratic form and hope that it gives you a refutation. Let me tell you what this precise scheme is going to look like. Now, the specific matrix I'm going to use is the new idea. Okay. So I'm going to tell you what this matrix is going to be. That's the so-called Kikuchi matrix. Okay. So what I'm going to do first is tell you how to take just this fragment of this polynomial, the sum over tuples corresponding to H sub I, and write it as a quadratic form of some matrix. Okay. And then I just, you know, take linear combinations to get the whole quadratic form. Okay. So here is the matrix. Very, very simple, no statistical physics required. The matrix is indexed by all possible subsets of size L of the code word bits. So n, small n, okay? L is a parameter, so at every level L, I have a matrix, right? And for level L, I basically have a matrix which is n to the L, or n choose L size. Yes? So it's indexed by sets of size exactly L. And now, it's in fact a 0, 1 matrix. It has an entry equal to 1 if and only if the corresponding row and column S and T symmetric difference out to a 4 tuple which is in 8 sub I. Okay. I'm good. So, notice that, this is, okay, so I'm going to use this matrix in a very extreme regime. I'm actually going to invoke the level L equals something like root of small n, which means that this is going to be an exponential size matrix, even though the formula I'm starting with only is a quartic polynomial, like a polynomial size object, I'm going to write it as a quadratic form of this exponential size matrix. Now, even though I'm going to invoke this matrix at a very large level, notice that this matrix is very sparse, right? If I take an edge, what does it mean? S and T have an edge when they symmetric difference out to a set of size 4, even though they are themselves set of size L. This happens if and only if they intersect in all but 2 elements. So the only kinds of edges are S and T, where they share L minus 2 elements, and the remaining 2 elements which are different combine to give you a 4 tuple in 8 sub I. It's a very, very sparse matrix. Excellent. So now, while we are doing this, we can also do some basic calculation. Each tuple contributes many different edges to this matrix because there are many different pairs ST with the same symmetric difference. And we can calculate exactly what these are. Let's not go into maybe calculations right now because I'm going to finish soon. But it's like very simple to calculate number that you can write down, right? And that number, in fact, also tells you what the average degree of this matrix is because, I know the total number of ones, right? So I can tell you what is the average number of ones per row. And it turns out to be something like L square over N, trust me. It's very, very simple. The proof is actually right there, but I don't want you to verify. Good. So now what? I have now established to you that this guy is a quadratic form of this matrix, right? The proof is very simple. Here's the vector I'm going to take the quadratic form on. For an assignment X, which is like an n-dimensional vector, small n-dimensional vector, take the vector of all L-wise monomials in X. So X to the circle L is simply the vector of n choose L size, where basically in entry S, I populate the Sth multilinear monomial in X. So it's an n choose L dimensional vector. If I take the quadratic form of this matrix A sub I on X circle to the L, what happens? Well, you might remember that's basically how you can expand a quadratic form out. And now what happens? XS and XT are plus minus 1 valued things. Product of plus minus 1 valued things. XS times XT is equal to XS symmetric difference T, right? Well, AI is, non-zero only when S and T is symmetric difference out to a 4 tuple. So even though, formally this is a 2L degree polynomial, only quartic terms survive. In fact, the only terms that survive are the ones that correspond to the 4 tuples I have. So hopefully this is not so hard to believe that up to some scaling, I'm simply going to get, the polynomial I'm interested in. So delta is like some fixed scaling, which also we computed earlier. Okay. So, what does it mean? I can write down this whole polynomial psi sub b as quadratic form of linear combinations of this matrices AI with coefficients b sub I. That's it. Okay. So far, so good. Okay. Now what do we do? Well, I'm going to use a spectral upper bound on this polynomial. What that means is that, I'm just going to upper bound it by the L2 square norm, the vector I'm taking the quadratic form on, times the largest eigenvalue or the spectral norm of the matrix sum bi AI. Okay. Now, so far we've not used randomness of B. This is the first time I'm going to use it. If B is random, well, this is a random signed sum of some fixed matrices. If I give you random signed sum of scalars, you would use the Chernoff bound, okay? And you would imagine that as long as the scalars were all small, so that, the linear form that you're taking this concentration on is like smooth, you would have exponential tails. There's an analogous fact that holds for matrices. I wrote it down for you. Okay. So fact 2 is what I'm talking about. If I have randomly signed sum of fixed matrices, the spectral norm basically looks like what it is in the scalar case. I take the variance term, which is like the sum of the squares of the matrices, but now it's the matrix, so I take the spectral norm, and then from variance to standard deviation, I have to take a square root. That's what I did here. The only difference is that I pay a square root log in the dimension of the matrix. That's the square root log. Okay, good. So I apply this inequality. I won't tell you the details of this anymore, but you simply use some very basic upper bound on A sub i's, like the spectral norm of A sub i's, which were like 0, 1 matrices. So that, spectral norm is upper bounded by just the maximum degree. With that, the computation is super simple. And, I'm going to skip the computation. and simply tell you what results from it, you basically get an upper bound on k. Remember, had lower bound, which is nk over 4. You get an upper bound, which has like a square root k kind of term on the right. If you resolve this, you basically get an upper bound of k. Okay, and the upper bound looks like some square of the the maximum degree of any AI divided by the average degree of any AI squared times log of the dimension of the matrices. Okay, so the point is that if AIs happen to be super regular, meaning all the degrees of AI are roughly the same, then D max over D average will be about 1, and I will get the upper bound of log capital N. Okay, log capital N, which is the log of the dimension of the matrix, is like log of n choose L, which looks like L log n. So the lower bound I get is like, or the bound on K I get is like L, the level, times log small n, right? On the other hand, notice that the maximum degree of this AI is always at least 1. There is an edge. While the average degree, we proved is like L square over n. If this is too tiny, there is no hope of approximate regularity because the average degree is like tinier than 1. So the only way I can have some semblance of regularity is if I make sure that the average degree is at least 1. So the least L, where this approximate regular version would make sense, is square root of small n. Okay, and the message is that even though you might suspect that this is too good to be true, with some very simple cleanup, you can ensure that each AI is approximately regular at L equals square root of n. So punchline is that this is the bound we get. K is at most square root of n, and that's in fact the best known lower bound right now for 4 query LDCs. I essentially gave you the complete proof. I was a bit fast. Sorry about that. That's the result we proved. And I'll maybe just summarize this whole method so far. So what did we do? We took a 4 LDC, made some polynomial out of it, took a polynomial for like random message. Then we constructed a certificate for it, and there's a certificate at every level of this Kikuchi thingy. As the level increases, the certificate's bound actually weakens, right? So we want to take like the smallest level where the certificate works. So the only heuristic, or the only thing that somehow decides what will end up from this whole scheme is what is the level at which the average density becomes at least 1. And that's basically root of small n for 4 LDCs, and that's where we win. Okay, good. So just to quickly end and tell you like one nugget of what happens for LCCs instead of LDCs. The point is that there are like additional matches, right? So you should be able to get like more constraints. And if there are more constraints, you might expect that the average degree of the matrices will be larger. So you may win. The issue with this approach is that even though there are more matchings, there are only k independent bits because the message is still of size k. So only the first k matchings come up with constraints with right-hand side which are random. The rest are like completely correlated with it. So what do? This is in fact the problem with all the previous things. They did not know how to utilize this structure. But to us, it is actually natural. What should we do? Well, I have a bunch of XOR constraints. I don't know how to use them like individually. I'm gonna apply resolution to them. So I take constraints from the first k matchings. I resolve them together with like constraints from the last n minus k matchings. In fact, I do like some long chain resolution. So I take like many constraints from the right hand side. And this way I get something with like random right hand sides, but that also uses the structure from the right hand side matchings. It turns out that with some sweating, this new instance of XOR formulas can be analyzed with the same method, and you can actually show that this density increases enough that you can actually get a certificate that works at level about polylog n instead of like square root of n. And that's basically how we get the exponential lower bound. That's all I'll say for the purpose of this talk. So many more applications like this. Sorry, I was a little bit fast, and sorry I didn't leave any time for questions.
You do have time for a couple.
So in this instance, you used the fact of evenness to say that, to define the matrix so that you get, size n minus 2. So what do you do in the case of 3?
Yeah, it's a great question. So, as Paul is already observing, for the case of 3, this matrix doesn't make sense. If I take XOR of 2 sets of same size, their symmetric difference is always even. So, this matrix is simply, senseless for like odd arity. So what we actually do is we apply this so-called Cauchy-Schwarz trick, which is like, we do one step of resolution. We take like triples that, intersect in one variable. If you do apply resolution, now you get like 4 tuples. The issue, of course, is that you get correlations now. You have to deal with them. That's the nasty part. But, you at least have like some evenality constraints for which you can take these matrices. So the difficulty is like, some correlations in the random matrix stuff, but, you can analyze them with some more work. That's the reason I skipped it here. Yes.
But why doesn't this work for 4 LCCs? What you just said? I mean, why does it only work for 3?
LCCs.
Oh,
Not
LCCs, yes.
No. Okay, sorry. Let me back up. I'm saying, if I wanted to do it for 3 LDCs, I would need to do one step of resolution to begin with. Because, I don't even have a matrix that makes sense. None of this is like, about LCCs. For LCCs, in some sense, the only idea we have is, how to use the extra constraints. Now, maybe the question you had was like, why doesn't this work for 4? Why is it 3?
Of course it does. It just also works.
No, it doesn't.
The resolvents are of size 5 when you do that, is that the issue?
Yeah, so like, what really is going on
Or
is
seven.
that when you like repeatedly, do resolution with the right hand sides, on average, every new constraint contributes 2 variables. So it effectively looks like, some kind of a 2 XOR system blown up. And because you have like exponential lower bound for 2 LDCs, vaguely speaking, you can expect some exponential thing to happen, which does happen with some work. If you do this for like, let's say 4, then the resolvents are of size 3 on average. And now, you are basically in the land of 3 LDCs. In fact, there is a formal reduction between Q query LCCs and Q minus 1 query LDCs. The issue is that our best lower bounds for, 3 LDCs are very weak. They're cubic. So you can improve the best known LCC lower bounds if you work through all of this. We didn't write it up. If you work through it, you can improve it, I think, by some polynomial factor, but you don't get exponential gains at anywhere except 3. So everything I said is really about 3. Sorry. Yes.
General question, is there a connection to the refutations, random refutations by Hsieh, spectral refutations by Hsieh and Oberwolfach?
Great question. So in some sense, we are like the earliest work was trying to answer their question, including like the Hsieh thingy. So the hypergraph mode bound, the conjecture is really like, one motivation for that was like whether Hsieh time, refutations exist for smoothed k-SAT formulas instead of just random. So one consequence of our confirmation of the conjecture, which I did not tell you about at all, like the first bullet point here, was, that we can prove that FKO reputations exist for smooth k-SAT formulas now. So yeah, so these things do have like consequences there, but I talked only about like 3 and 4 today.
When you say resolution, you mean Gaussian elimination, do you? Linear equations.
It's like, I'm deriving like in a very specific combinatorial format. So I'm going to take like, some set of constraints which look like a chain where, every consecutive thing intersects in one variable.
But you're taking XOR of them, right?
I'm taking XOR of them.
So it's Gaussian elimination, sort of. I mean, you're deriving new linear equations.
It's XOR resolution as in like one of the talks yesterday. But yes, you can call it Gaussian elimination.
Yeah. Okay.
So by smooth, just to remind us about the smooth k-SAT,
Right.
What do you mean by that?
Right. So smooth k-SAT formula, I did not define it for you. Here what I mean, you start from a worst case formula, an arbitrary k-SAT formula. Now for each literal, you flip it independently with probability, let's say some small constant like 1 in 100. That's the smoothing process. You start from an arbitrary formula and then you perturb every literal independently. If there are like many more than n clauses, this perturbation would almost certainly produce an unsatisfiable formula. So you can ask for a refutation. And you can see that in some sense, the clause structure in this formula is completely arbitrary. We don't have any control over the k-tuples that appear. The only randomness is in the literals. And the question is like, do the refutations that we know exist for random k-SAT also exist here? The punchline is that all the things we know about random k-SAT, including this non-deterministic refutations, are true with exact same bounds, even for smooth k-SAT. That's like the result number 1 here, which I did not tell you about.
All right, let's send the speaker again. Let me make it right.